So this is a joint ongoing work with Alexei Oblomkov, Richard Rimani, and my graduate student Li Han. And this is unfortunately half-baked, but I think nevertheless interesting to discuss. So let me begin with very well-known facts and constructions. You consider Cronheimer, Nakajima quiver varieties and their various types of homology and coherent sheaves. And these varieties are known to be related to the Reshetikhin-derived polynomials and link homology, and also to the action of quantum Lie algebra SLN on the tensor product of exterior powers of the defining representation. And the question that I'd like to address today is how to generalize these well-known constructions in order to cover also super-algebras GLMN. And what else does string theory suggest? So an example of these geometric categorifications, maybe the simplest one, comes from the cotangent bundle to a Grassmannian, whose quiver is presented here. So you have CM, CN, homes from CM to CN, homes from CN to CM, and the condition for the moment map here. I will remind about this a little bit later. And this variety is related to two things simultaneously. The weight space of a tensor product of n fundamental representations of GL2, and the weight being m n minus m, and also the isomorphic space, the space of the same dimension, the weight space of GLN, corresponding to the weight 1, 1, 1, in the tensor product of two exterior powers of size m and n minus m. They're the same. So the action of the universal enveloping algebra happens on the left side of this isomorphism. So for, say, for two Grassmannians in the same CN, there are functors between the categories of coherent sheaves that correspond to E and F of GL2 acting on the weight spaces. This construction was discussed in details in a paper by Kautis and Kamnitzer. The right-hand side of this isomorphism, known as skew-Howe duality, gives you the annular homology of a two-strand closed braid. This red line denotes the whole of the annulus. And so you have braid lines going up. So if you want to construct a homology of the unknot, you consider this Grassmannian. So the left strand carries the mth exterior power, and the right-hand strand carries n minus mth exterior power, which is isomorphic to the dual of the mth power. So you can replace this line with this line. And then you can close you can put a cup and a cap. And so the homology will be computed as a composition of two functors from coherent sheaves on a point to two strands, and then two coherent sheaves on a point. Again, this is a very well-known calculation. Would yield the standard homology of the unknot colored by an exterior power. So you see that on both sides you have two different partitions of the same number n. So a general version of this story is that you have two ordered partitions of the same number n. Let me call it mu and lambda. And to that data you associate a quiver variety, a symplectic variety, which is whose coherent sheaves are related to either this, the weight of GLL for mu's, or the weight for GLM for these lambdas. So these are the same. And I will comment later about why it's clear that the dimensions are the same from simple combinatorics. So the goal is to generalize this to GLL1L2 and GLM1M2. So in order to explain this generalization, and I talked about it in a year ago, but with a slightly different emphasis, let us quickly recall the construction of these Kronheimer-Nakajima quiver varieties in the arrow bow presentation. So quick reminder, if X is a symplectic variety with Hamiltonian action of the group, this means that there is a so-called moment map from the variety to the dual Lie algebra, such that for any Lie algebra element, pairing this with this Lie algebra element gives you a function on X, which is a Hamiltonian for the vector field corresponding to the Lie algebra element. So the Hamiltonian reduction of X with respect to the action of G consists of two parts. You take zeros of the moment map and then take the quotient by the group. And then you get another symplectic variety. This is the analog of quotient in usual topology. So today we'll identify GLN and GLN dual by the killing form, so I will not distinguish them. So here is the quiver construction category style. In fact, it's a 4-category, but just let's keep that in mind. An object of this category is just a number n, or a group GLN. And here I'm simplifying. I'm ignoring certain delicate points, but generally it's correct. A morphism is a symplectic variety with the action of GLM cross G, with the Hamiltonian action of GLM cross GLN. So you have two moment maps. And a composition of morphisms is just a joint Hamiltonian reduction. You multiply them and you reduce at the middle point. The net result, if you apply it to a quiver, to a quiver which is a line, AN type quiver, from 0 to 0. I will include zeros at the end for some reason. Will be just a quiver variety. So there are no groups, GL0 and GL0, and the composition gives you some symplectic variety. So this way you can construct AN-type quiver varieties. There are two types of elementary morphisms in this 4-category that generate all interesting morphisms. One type is the arrow morphism. That's the old age of, in Nakajima, Kronheimer-Nakajima construction, two arrows. So it represents cotangent bundle to home from, cotangent bundle from home CM to CN. And then there is also a bow morphism, I think introduced in two places. It was introduced by Cherkis and some other people with different interests on the algebraic geometry side. I'm sorry, my references are incomplete, so I apologize for not being more precise in the story of this. And it wasn't invented by me or by us. It's an old story. So the bow morphism has this tooth shape. It looks weird. From the string perspective, every arrow here makes a lot of sense. But if you look at it, it's really unnatural and weird. So there are homes from CM to CN, from CM to C1, from C1 to CN. There are two endomorphisms of CM and CN, these two, and there is a condition that the commutator of phi with these y's is equal to the composition of V and W. And surprise, surprise, this is also a symplectic variety with the natural action of GLM and GLN twisting all these arrows. So two facts. if you have these n of these teeth with the same numbers n at the bottom, then you can compress them into the standard quiver picture with a framing. So these bow edges create a framing. And the fact number 2 is that you can, the so-called Hanani-Witten move, you can switch the order of arrow and bow, and if you place a different number in the middle. The rule is very simple. Define a local charge of an edge as right minus left. So m minus L and minus m. If you switch them, then the charges, local charges, are almost the same, except you have to add 1 to one charge and subtract from the other. So that's the numerics of the Hanani-Witten move. So the advertised quiver variety for the tensor product of exterior powers, the weight space in the tensor product of exterior powers, can be constructed in the following way. Move all the arrows to the left, move all the bows to the right. If you compose the arrow edges, then you end up with a variety with the action of GLN. And that will be the cotangent bundle to a partial flag variety. It's very well known. And if you combine these teeth, you get what's known as a Henso quiver. Then you will get something. It's called an equivariant Slotowitz slice. Roughly speaking, and I'll come back to it a bit later, you take a nilpotent matrix of GLN with the blocks of the sizes corresponding to deltas of the bow edges, and you take a transverse slice in Lie algebra to its orbit, and multiply by the group. Surprise, surprise, what you get is, again, a symplectic variety. So a transverse slice to an orbit times a group, you get a symplectic variety. You do a joint Hamiltonian reduction in the middle, and you get the required quiver variety. Again, in all story, one would move bow edges to the left by using Hanani-Witten move, so as to make their deltas equal to 0. And then they will turn into framing. So by using Hanani-Witten, it's easy to bring it to the good old form. But in this form, you can quickly read the sizes of the columns and the weights of the group, because they're just local charges of the edges, left minus right or right minus left. So on the topology side, as I said, each edge A represents a representation, an exterior power, and each bow edge represents a weight. So if you want to get the 0 weight for the purpose of closing your braid up and down, then your bow edges would have to have the same delta, so that the SLN weight would be 0. Note one thing. If you take an arrow edge to the left of L bows and move it all the way, then the local charge will change from delta plus to, if you take the opposite sign, will be L minus delta plus. So you will get the conjugate representation, at least naively, by its charge. So this allows you to create conjugate representations by placing the conjugate column here. It will be the same as conjugate if you move it to the right by Hanani-Witten. And this is a little bit misleading because it doesn't work in the generalization. So in order to get to, so the story is about 4 category, and it is a little bit too good. When you do categorification, you always get sheaves sitting on Lagrangian, whose support is Lagrangian subvarieties. And this is an indication that with these varieties, you should build a 2-categorification rather than categorification. For super-algebras, there will be just a categorification. Yes?
When you say Hanani-Witten move, do you
Hanani-Witten what?
Hanani-Witten tradition, is that the same thing?
I guess so. So you just switch the order of arrow and bow. NS5 and D5 or D4. Yes. I'm sorry, could you push the microphone?
So you said this is a 4 category, right? And I'm wondering what, like...
If you ask me after the talk, I'll be very happy to comment, at least naively. Or I can refer you to the papers by Gayotto, Moore, and Tachikawa about symplectic varieties, variety value two-dimensional QFTs. But again, I'll be happy to comment at the end. So we have to reduce by 1 floor in order to get to GLMN. That's the idea. And so here will be an alternative construction of the same varieties, which is at the next level down. So an object is still N, but it's related to a commuting variety. This is the quiver of the variety, represents cotangent bundle to GLN reduced by the adjoint action. A morphism is a pair, an auxiliary green variety X, and a function on X cross GLM cross GLN. See these 2 arrows. I call them XR and X left and XR, and the function should be invariant with respect to the action of GLM and GLN. So that group acts on green X and also on this and on that by conjugation, and the function should be invariant. So this is a morphism. The reason why this is a morphism, and I don't want to go into details, is that it represents a Lagrangian correspondence between 2 such varieties. So it's a different symplectic story. And again, it looks like the way to represent a Lagrangian subvariety or Lagrangian correspondence in symplectic algebraic geometry is to use the description by functions. You can describe a Lagrangian in a cotangent bundle by a function on the base as a graph of its differential. So this seems to be the right way to define a Lagrangian subvariety in algebraic geometry.
Sorry, are you saying in this category we're only supposed to think of objects that are the commuting variety for GLN? Like
no.
Oh.
No, you can consider more general quivers, and I will try to mention it at the end. So one of the generalizations of the story, the story is just a first small step in a certain direction.
Okay, thanks.
So one generalization is to replace this, for example, and what we did with, and we're doing with Alexei Oblomkov is to use a Hilbert scheme instead of this one. That's how we were constructing link homology.
I have a question. I'm guessing W is a potential function. Why is it GLM plus GLN invariant?
You have to, and I'll give you an example in a moment of this. So old versus new. The old story is a symplectic variety with GLM cross GLN. So in the new language, it becomes the auxiliary variety. And the function is take right moment map multiply by the right matrix, left moment map by the left matrix, take the trace, and take the difference or the sum. A composition of morphisms looks very simple. All you have to do is take the product of the auxiliary varieties, also add that loop that was in the story as an extra auxiliary variety, take the quotient by the group in the middle, or just say GLN equivariant for whatever you will be using it for. So keep it in your records that there is this GLN action, and add up the superpotentials. I will refer to W as superpotential by its physics name. I'm sorry, could you speak louder?
Yeah, so I did push the button, but it takes a second. But for the higher maps in the 4 category, are they like invertible maps or are they non-invertible maps?
So I will, let me put this off to the questions, because I want to get to GLMN, but I will come back and comment on this for category. It was a teaser, and
Yeah, I mean, I didn't want to know, like,
so a morphism, home between two morphisms
Yeah.
will be two category
okay,
in
proper
the
two
old
category.
story,
Okay, yeah.
which is one floor above what you need for the usual constructions. So if you compare the composition, the old composition, which was the joint Hamiltonian reduction, and the new composition, you see that in the old one, you set the moment maps equal to each other. That was the joint Hamiltonian reduction condition. And in the new story, you take their difference and multiply by the extra matrix X, the auxiliary matrix X. So X serves as a Lagrange multiplier to impose the condition that the moment maps are equal to each other. That's the meaning of what goes on. So the net result in the new story, you go from 0 to 0, and what you end up is the auxiliary variety. Here and here there is nothing, just points. So all you get is the auxiliary variety with the action of the big, big group from all the nodes, and the big, big, big superpotential invariant with respect to that function. So this is your new data. And the relation with the old story for the relevant quivers is that the old Kornheimer-Nakajima quiver variety is the critical locus of this W on this bigger X tilde. Again, X tilde is bigger because you do not impose the condition that moment maps are equal. You keep them separate. So after you impose criticality, they become, this one reduces to this. And moreover, the coherent sheaves over the quiver variety is the same as the category of matrix factorizations, something equivariant with respect to the total group on this bigger variety with this W being a superpotential. So don't turn off. Good news is that in the examples that we consider today, there will be no need to consider matrix factorizations, because if W has a good critical locus, good meaning it's smooth and the matrix of second derivatives in the transverse direction is non-degenerate, then this is the same as coherent sheaves on the critical locus. So just ignore and take coherent sheaves on the critical locus. And more generally, if your X is the total space of a vector bundle over some X prime, and you have a section in the dual vector bundle, then you can construct a function on the total space that is linear along the fibers, just pairing with that section of the dual. And so if this one is your superpotential, then the matrix factorizations is the same as coherent sheaves on the zeros of that section on the base. Except not quite. You again have to impose some condition that the zeros are good. And if the zeros are bad, then this would be the right choice to describe the category associated with the quiver. So if you end up with this kind of description, then you can say coherent sheaves, but you would have to say derived zeros of mu. So when you hear derived Steinberg variety, it's because of this. Yes?
So because of this discussion of good locus, so this box, this red box, is it a theorem or is it a theorem for certain lambdas and mu's? And if yes, for which?
I have to be careful. I have to be careful. So this is the theorem for good ones that really represent the weight spaces. You can make it bad.
So that's for some certain lambdas and mu's, right?
Yes.
Not every.
Yes.
So,
So
can you describe which lambdas and mu's satisfy the condition?
So if the condition is not satisfied and you construct a quiver with bad critical locus, then this is the right choice, in quotes, for the category of coherent sheaves over some bad quiver variety. So for example, an important quiver variety is the equivariant Steinberg variety associated with the group. And if you read Bezrukavnikov-Risch, for example, they will say the right Steinberg variety, and that's because their construction is equivalent to doing matrix factorizations. So we will not need this in its the full story. So let me get to the essence of today's story. The extension of the construction of quiver varieties allows us to have more general morphisms as compared to the old ones. So what we need is a Legendre transform of the old edges. Legendre, if you Google Legendre transform, it says replace a function f of x by negative f of y plus xy, function of two variables. You trade one variable for two. What it does, this transform, very quickly, if your f of x describes a Lagrangian submanifold in a two-dimensional space as a graph of the differential of f of x, then the new function, with y being interpreted as auxiliary variable, will describe the same Lagrangian submanifold flipped across the diagonal. So now the derivative of the new function with respect to x will give you x instead of y, so to say. So you're flipping the Lagrangian submanifold of a cotangent bundle to a vector space. Just change coordinates and momenta. That's what Legendre does. And the coordinates and momenta refer to the hidden commuting varieties at the ends. So formally, what we want to do is take an old h, x and w, and make it bigger. So we get two more auxiliary GLs and a new long superpotential, according to what Wikipedia tells us to do. So this is the trick. Looks bulky, but conceptually it's easy. So this is an autoequivalence of this free category. If you do it twice, you just switch the signs of the vector spaces. So back to quivers. What do we want? We want to include new generators, the Legendre transforms of arrow and bow. In fact, if you look at the original bow, you see these two loops. So the original bow is almost a Legendre transform of something simpler, except there is a stability condition involved. So it's not quite a Legendre transform. Warning, there are no Hanani-Witten moves if one of them is flipped. If both are flipped, then this is an autoequivalence, so you can still move them. But if one is flipped, you cannot. So the order matters. In previous story, the order of bows and arrows didn't matter. You can move one through the other. An example. If you combine arrows from 0 to some number n, you get a cotangent bundle to a flag variety. And your W is moment map paired with xn sitting at the last node. If you flip, and what is the cotangent bundle to a flag variety? Its points are pairs, a flag and a matrix. And this matrix preserves the flag in a nilpotent way. So every flag subspace has to go to the next one sitting inside it. So it's a nilpotent condition. But if you flip some of the arrow edges, then the nilpotency condition is replaced by simply preserve. A subspace has to go to itself. It doesn't have to go down. So it's a bigger one. So now we want to consider quivers with arrows and bows and flipped arrows and flipped bows. To interpret the variety that comes out of it and relate it to representation theory, we have to observe that we're dealing with at least 4 types of representations. So there may be more, there may be some Verma modules, but I don't know I'm not sure about that. That requires some study. So for GLMN, there will be 4 representations. CMN, the standard one, its odd version, CNM, where you switch the parities. The dual to this, which is not the same as this, and the dual to this. So 4 types overall. If you're dealing with GLN0, which is a particular case of this, then the standard even representation is this dotted box. Its dual is its dual. The odd one is the box of the classical representation theory. It's the odd. And the dual odd is the same as n-1 boxes, on the next to top exterior power. So the slogan, again, coming from physics, is always symmetrize, not skew symmetrize, but symmetrize. The representation theory tells you that the best ones are the exterior powers. But in fact, the physics tells you that the basic ones, but they're not as good maybe, are the symmetric powers. But if you do it in the old GLN0 picture, then they're odd. So symmetrizing, you're super symmetrizing. Symmetrizing taking into account the parity. So symmetrizing the odd gives you skew symmetrizing. So when it comes to symmetrizing the undotted ones, I'll draw it as a column. Although the honest way to present it would be a row. So then it will be easier to relate it to the standard picture. So symmetric, these are even, and symmetric odd, which means you're skew symmetrizing them. So now let's look first for topological applications and then for the representation theory applications. So if you want to construct a homology of a link related to GL L1, L2, present your link as a closure of a braid, as usual, and then you have to introduce categories for each slice and the functors corresponding to the braiding and to cups and to caps. And part of it should be easy, but part of it requires a lot of work. So I will explain some baby examples how this works. So generally, what is this category? It's a 3-part quiver. The arrow edges corresponding to the strands going up are on the left. So that's your old cotangent bundle to flag, or this mixed bundle where you have, sometimes you have preserved the subspace and sometimes you have lower it by 1 step. Then, for the purpose of topology, you have some bow and bow flipped edges with the same number n, because I want the 0 weight. I want to close it by cups and caps. That's why these n's are all the same. And then you have to represent the arrows going down. So I have to place some arrow edges on the right. The reason why going up is on one side and going down is on the other side, again, comes from physics, where people said Sergey is the authority on who said that first and introduced it. So again, this is an old, amazing story of string theory related to Chern-Simons, Witten-Chern-Simons. The story was, take cotangent bundle to 3-sphere. And when you have a knot, take a conormal bundle in the associated conormal bundle in the cotangent bundle, conormal to that knot. And then people said, push that away from the 0 section. So there are two directions in which you can push a conormal bundle to a knot because of counting the dimension. There is one direction you can push it up or down. And if you determine that by the direction of the strand, then this is what you end up with. So this is related to pushing things over the zero section in T star S3, at least in my understanding of the things. Anyway, if you're dealing with A, and there are no flippings here, it doesn't matter whether it's on the left or on the right. You can use Hanani-Witten and move. And so if you have 1 here, this one should be n minus 1, but you can move it, this one should be 1 going down, but you can move it through and it will become n minus 1. So you will pair 1 and n minus 1, the old story. In the new story, you cannot do it generally. You cannot move it through, so you have to keep it on the right. So 3 examples for an unknot colored by a box, for GL20, for GL02, and for GL11. So I'll show you the calculations with these very simple baby quiver varieties and compare them with what comes from Hilbert's scheme of 1 point on C2. The idea that the homology should be related to this is old. I should refer to Eugen Gorsky, Jake Rasmussen, Alexei Oblomkov, and Sergei, of course, in relation. So at some point, the idea appeared that you should introduce a differential in the triply graded homology, and that differential will reduce triply graded homology to, Jake played a big role in this, to GLMN. So the idea for GLMN, I'll show you, is this. So you have two polynomials of one variable related by this differential. But y is equal to 0 on C of x. So this differential is 0 unless L2 is 0. But it tells you what is the grading shift. So in the interesting cases, new cases, I'll be getting C of x and C of x with a relative grading given by this counting. So we're matching the relative gradings here. It's not too much, but nevertheless, it's something. So this is what we want to get. So the old story, so the general story is the middle will be some x, maybe singular, and going from nothing to 2 is tensor with some sheaf, and going back to nothing is derived tensoring with the same sheaf and taking homology. This is how it works. So GL20, this is your quiver. So you get T star P1. And for GL11 and GL02, you get something new, in quotes. So in all 3 cases, you can say that this extra variety, that this bigger variety is the Grafendieck-Springer resolution of GL2. I'll show you in a moment what that is, but with different W's. So all 3 cases give you the same big one, but different W's, and very, very similar sheaves E. So this big variety is take P1, and on top of every C1 and C2, put the 2 by 2 matrix that preserves it. Just condition of preservation. So this bundle splits into 2 O-1s and O0 that you can present just as a separate C, because we're interested in the total space, not in the bundle per se. So explicitly, we have the following picture in all 3 cases. C1 with the action of GL1, C2, and one arrow going here, x1, x2, not equal to 0 simultaneously, and arrow back, y1, y2, and an extra C. So in the old case of GL20, your W is this, Z is the coordinate on extra C. So this is your Lagrange multiplier, so you say that this is the moment map is equal to 0, so 2 O-1s are reduced to a subbundle O-2, you get the old story. The 0, 2 part is, the superpotential is just 0. So this is your x, your bundle E is still O minus 1, same as you used here. But now it sits in on the 0, this bundle is supported on the 0 section of the resolution. So the fibers are different, so you get a different resolution out of it. And there is an extra C of Z. So you end up with the right answer. If you compute the degree shifts, the action of C stars on this, I'm just ignoring it, you do get the right answer. And the GL11, where you flip one bow and do not flip the other, gives you superpotential ZX1, Y1. So you kill only 1/2 of that moment map. If you interpret this as Lagrange multiplier, then instead of x tilde, you get just x. But it is singular. So what is your x? You have P1, and you have a fiber of one of O minus 1s, just one fiber attached at the North Pole. So it's a cross singularity, xy equals to 0, and another O minus 1 hanging over it. Going from nothing to 2 strands is O minus 1 sitting on the 0 section of this. And if you compute its store with itself, indeed comes out the homology, the GL11 homology of the unknot. The polynomial part of it will come from the resolution of this sitting on the 0 section when you have an extra 1 attached. Try C of xy modulo x times y, and how would you resolve C of xy mod y? In the xy equal to 0, you will get an infinite resolution, semi-infinite, and that will be the source of polynomials.
Yeah, T star P1, you would have an attracting set for C star action. That looks like
Say it again?
in T star P1, you have a C star action, and the attracting set is the P1 and the line that intersect.
It's not related to. It's the whole thing. The story about attracting sets is separate. Also happen, but it would be a separate story. Can also be played in this setting, I think. In fact, that's what we did with Richard Riemann.
It's not the same geometrical object, it's something else.
Let me comment here. So it seems to work, and the key step for us was to recognize that you have to keep some arrow edges on one side and some arrow edges on the other side. And that will allow you to create dual representations. The good feature of fundamental representations of exterior powers is that dual is also an exterior power. If you're dealing with symmetric powers, then the dual is not the same row. It's the row of dual boxes. So the way to do it is to push them to the other side of the quiver and get the right variety for this. So now, very quickly, the representation theory story. Again, this requires an honest work, but at least we can propose a variety and consider a baby example of GL11 acting on a tensor product of 2 boxes. That's what we calculated so far. So again, you need a 3-part quiver. Now, the arrow edges represent the weights, and the bow edges represent the boxes. So now, bow edges are on opposite sides. If you want to categorify tensor products of symmetrized and their duals, so then you would have to put them on both sides. Let me quickly comment on what happens if you have arrows just, if you have bows just on one side of the arrows. Let's ignore the other side. It's still interesting. So you're categorifying weight spaces in the symmetric tensor powers of of the defining representation. Let's ignore the dual ones. So the combinatorics is this. You have boxes, some are symmetrized, some are skew-symmetrized, and you have a supply of weights. So you have, consider weights as an objects, balls in urns with fixed numbers, and you have to place them here, but with the condition that two odd weights cannot appear in the same, how should I say it? Two even ones cannot appear in the same column, and two odd ones cannot appear in the same row. So there is an exclusion principle. So if here you have two even weights, you cannot, of the same nature, two representatives of this, two weight vectors of the same weight, you cannot place them in the same column because they will be killed by skew symmetrization. And you cannot place two odd weights in the same row. So how does it come about in geometry? So in geometry, we have a bundle over a flag variety where the matrices either preserve the subspace or send it down versus a nilpotent matrix. You see, to make the geometric story simple, let us at least naively count the fixed points of an action of some torus over this variety X. So I will just tell you how these fixed points look. You have to take the nilpotent matrix for which the slice goes. So this is determined, let's say, by, again, depending on how you want to view it, this is determined by the weights. And you have a standard flag, meaning a flag composed in the natural way out of the standard basis vectors. And there may be a permutation of basis vectors. So this is a permuted standard flag comparing this matrix to this flag may involve a permutation of basis vectors. So now you impose a conditions. Suppose you didn't flip any bow edges to make it simple. So suppose all your representations are powers of fundamental without a shift. Then these matrix elements have to either preserve the flag or send it down. So if you think about this combinatorics, you will see that it matches exactly the combinatorics of two types of balls and two types of boxes, trying to match a flag with this matrix. If you flip the bow edges, what happens is that in the corresponding Jordan box, so each box corresponds to a bow edge. In the corresponding Jordan box, you have to impose a condition that it violates the flag condition. So if you, say, flip this box, everyone has to either take the flag outside to the next one or to preserve it, depending on what was the original condition. And so with this, you will match the combinatorics of taking powers of CMN or CNM. So that's the geometry, matching a nilpotent matrix with a permuted standard flag and looking at the permutations that are allowed in this way. So to finish this story, let us look at the functors that give you the action of E and F. So let us just go to the SL11 case. It will take me 3 minutes, and I will finish. So what is the classical story of the superalgebra SL11? There are, in this algebra, there are two odd, I will describe its action, the action of the generators on a standard on the defining two-dimensional representation. So there is E and F, same as SL2, except that you consider they're anti-commutators since they're odd generators, and it should be equal to the identity matrix, which is not an identity matrix. It's an element of the super Lie algebra. So it won't be 1, 1 always in all the representations, but it is in the center anyway. So this is how the algebra works. Now, I'll say physics suggests the superalgebras, I think, came up first in the work of Gayotto and Witten on the walls, maybe even before that. So physicists saw this, and here is what physicists saw. First, what you see, I call it SL111, is the version of SL11 in each E and F simply anti-commute to 0. In this way, the category of representations of such SL11 is the same as this. So here you have 1, here you have 1, you have one GL1, and you have another GL1, and here you have 2 arrows representing E and F, only the arrows are even. But Cazul duality tells you that an even arrow you can trade for an odd arrow by Cazul duality. So this is how it happens in physics. Superalgebras first appear in this form. And this is the arrow edge, of course. But then when you do Q deformation, the anti-commutator becomes this. So the non-trivial anti-commutator comes together with the Q deformation. The details can be found in a paper by Kapustin and Saulina, where this is explained somewhere in the middle. And this is what we see. And this was seen before by, Alexei will remind. So when we use the quivers, what we see is that the lowest weight, so we consider tensor product of 2 two-dimensional representations of SL11. And again, there are 3 weights, same as SL2. The lowest one, this is the category of a point, sheaves on a point, vector spaces. The next one is the coherent sheaves over the resolved conifold. This is really ubiquitous, same as T star P1. If you deal with GL11, you will always see this one showing up. And the top one is coherent sheaves over the full algebra GL2. And it's easy to explain why these show up. E and F are, again, tensoring with O minus 1 and simply pushing forward along the Grothendieck-Steinberg resolution and the adjoint functors. So this is what E and F are. So what do we see? We see that E squared, indeed, is 0, because O minus 1 has no sections or cohomology. That's how it comes about. And same for F squared. And as for EF versus FE, we see indeed that the answer is not quantum 4, or not quantum 2 as you would expect, but Q to the 4 minus Q to the negative 4. So there is no denominator. The way it comes about is that, for example, you can say that there is a quasi-isomorphism of 2 complexes. One complex is this composition and the identity functor, and the other complex is identity functor in this composition with some shifts. So nothing splits. In the remaining one. So after this long story of flipping edges, where do we go from here? So bright perspectives, so to say. What makes sense? What does physics suggest? So first of all, consider more general quiver edges, the ones that are not symplectic. If you replace 1 in the tooth by k, it's no longer symplectic, but can be accommodated in the lower version of the story, this tooth. Why does it has physical meaning, has to be explored. Hope Sergey will help us. It's a project of giving it a proper explanation. If you take the standard cotangent bundle to flags and put 1/2 0n with a flip, the variety will be the composition of Heike correspondences used by Kautis and Kamnitzer. So it does make sense. Number 2, more general hidden quivers. That was the question. Instead of using commuting variety hidden in each node of the quiver, you can use other quiver varieties. Makes sense from physics perspective. Is presumably related to the following. Instead of studying quivers per se, I think, again, Sergey may comment more, one should study, at least try to study for the purpose of categorification of geometry, of topology, one should study coherent sheaves and quasi-maps from P1, and not exactly P1, two P1s with the cross at zeros, into Higgs branches of some interesting physical theories, which may be given by quivers. The quivers that we saw before are of this type. And there is a general principle that very often the spaces of quasi-maps can also be described as some other quivers. So there is a prime quiver and secondary quiver. So these are of high interest. I guess that coherent sheaves or quasi-maps will come out as matrix factorizations, and that will take care of the singularity of these spaces. And final comment, to categorification of simple roots. You see in Kavanov-Lauda-Rukia categorification of GL2 and beyond, some fundamental relations in the algebra were given by split complexes. EF minus FE didn't give you a complex. It splits. EF equals FE plus something. There is an unexpected split, similar to what you get for Kazhdan-Lustig objects for Hicke algebra. So it seems that whenever you get an unexpected splitting in categorification, this means that you can categorify one floor above. So there is a two-categorification. This is something Alexei and I worked for a long time, but it involves some technical difficulties. The main idea, how do you tangle them above? What is E squared in the case of GL2 acting on 2 times 2? You go from point to zero section of T star P1 to a point. So if you do it at a two-categorical level, the composition will be coherent sheaves over P1. They have a semi-orthogonal decomposition into, say, generated by O0 and O1. So if you go down, then this semi-orthogonal decomposition becomes a direct sum. So the key to two-categorification is considering semi-orthogonal decompositions, first used in this context, I think, by Orlov. If you have two categories related by functor, you can tangle them together. So if you transfer this to this symplectic setup, presumably you will get two-categorification when in ordinary categorification you have a split. Have to stop.